Okay, we're going to talk about solving equations, systems of equations, but actually matrix equations. So our goal is to solve this kind of equations where this is a matrix, column vector, another column vector. This is fixed. The matrix is fixed, and X is what we are solving for. This has a strong relationship with this other equation. So this is a different equation than this one because B is not necessarily always zero. However, when we solve this equation, that can help us solve this other equation um, in a big way. Let me first talk about solving. So solving in math means finding all solutions. And the key here is in all. So not just finding one, but finding them all, absolutely every one of the solutions. So whenever we're solving a problem, it is understood that we mean finding every single one of them. And that's why we need to know this. Um, we could find one solution, but we're not interested in one solution. We want to find all the solutions to this problem, and that's why this is necessary. Let me give you an analogy to this. If we have this is a very, very simple differential equation. When you have an equation where a derivative is involved, that is called a differential equation. This is super duper simple. So pretend that's a function of x. And if we want to, so this is back to calculus. This is just an extra example. Um, I'm just going to divide this because that's a different idea. And let's just label this as example 0. Okay. So if we're given this problem, what is y equal to? So we want to find all and every one of the functions whose derivative is equal to 0. Well, those functions have to be constants. So, y could be 13 because the derivative of 13 is 0. Or y could be pi because the derivative of pi is 0. Or y could be 51. Why? Because the derivative of 51 is 0. The derivative of any constant is 0. So we generically give the answer this way. So y is a constant, any constant. So C represents any constant. And by doing this, we're giving billions and billions of solutions because this number is a generic number and it could be 13 or pi or e or square root of 2 or -7, you name it. It can be anything. So here we are actually providing every one of the solutions with this. Okay, so this is, let me label this as A. Let's say you have a second problem, y prime equals x squared. Yeah, so we want to solve now this equation, this differential equations, which means finding the functions y so that when we find the derivative is x squared. Well, you have taken calculus too, so you are probably remembering we can use the power rule. So this is x cubed over 3 when we are trying to find the antiderivative. But then we always add a constant, which happens to be the solution to this other equation when this is equal to 0. So we always add all the solutions to this equation. This is a single solution, and that's how we obtain all the solutions. So this is a particular solution. It's not all the solutions, but it is a particular solution. And this is the solution to when the problem or the derivative is equal to 0. That's called the homogeneous solution, or the homogeneous solution. When we have the left side equal to 0, in this case, the solutions are called homogeneous. So this particular solution plus the homogeneous solutions gives us all the solutions. So together we have all the solutions. Now, there are many particular solutions. So we could have if somebody said y equals x cubed over 3 plus, I don't know, out of the blue, 7 plus a constant, technically speaking, that is correct, um, because this is a particular solution. And so when we find the derivative, why is it correct? Because the derivative of 7 is 0. So that is not adding to the problem. You know, when we find the derivative of this, we still end up with y prime equals x squared, which is this guy, because the derivative of 7 is 0, and so is the derivative of the constant. So this 7 is not messing things up. However, we don't call this a simplified solution because the 7 is unnecessary. This is simpler without the 7. And again, I took the 7 out of the blue. If somebody else said, how about 17? Still, this is unnecessary. The constant already takes care of any extra constants that may show up in here. So this is unnecessary. And consequently, this is not the best way to write the answer. If I was teaching calculus 2 and a student gave me this answer, I would take maybe half a point off, maybe a point off, depending on how many points the problem is, because not necessarily because the answer is technically wrong, but because the answer is not simplified to its ultimate simplification, which is part of the problem. We have to provide all the solutions in the simplest form. So so again, this is a particular solution, but we don't like this solution as part of providing all the solutions. We refer back to the one where the constant is 0. So where the constant is 0 is the one that we prefer for the particular solution. This is another particular solution. So this is another particular solution, but is not the best. Not best one because it is unnecessarily bigger or complicated. I know this is a small complication, but if the problem was had more things in it, then this could cause more complications and unnecessary things that we don't need. So that's why this is not the best. So when the possible constant, when there's a possible constant that we could add to a function and still have a particular solution, we just choose the constant to be 0. And that makes everything simpler. Okay, so this is calculus. We were solving this. We come up with a particular solution. Together, we get all the solutions to this problem. So this is called the homogeneous problem. This is the non-homogeneous problem, or a non-homogeneous problem, because there's many non-homogeneous problems. And the way we solve that problem is by providing a particular solution plus all the homogeneous answers. Very, very important. Well, that's exactly how it's going to happen here with matrices. You're not be given this. You're going to be given the non-homogeneous. This is called a homogeneous problem. Same names. If we have 0 here, we call this the homogeneous, and this is a non-homogeneous in general. Even if B could be zeros, we still call this non-homogeneous because we do not know in advance whether this guy would be all zeros or not. So this is the non-homogeneous. We solve this equation to get a bunch of answers. Now, there may be more than one constant involved in the answers, but that's okay. A bunch of constants or an infinite number of solutions driven by a constant, by a parameter. We find one particular solution with as many zeros as possible. And then we combine the two, and that gives us all the solutions for this. That's exactly how we're going to proceed. Now, in the, I wanted to say best case scenario. I don't know what best represents. Best is a relative term, of course. But in one case, I don't know if it's best, ideal. Let's label it ideal, but it's not necessarily ideal case. Okay. When you have ax equals b, and you are solving for for x, well, we can think of doing this by undoing what a does. When we have a regular, go back to algebra 1. If you have 3 plus x equals 5, how do we solve this equation? Well, we subtract 3 on both sides of the equation. But that's really the same thing as doing negative 3 plus x equals negative 3 plus 5. So by doing this, we're actually being a little lazy and not putting the negative 3 on a new line, which that's the way we should technically be doing this. So negative 3 plus 3 is 0. And if we go blow by blow, we would have 0 plus x is equal to, and then we can put together that, but 0 plus x is the same thing as x, so x equals 2. So there's the solution. Of course, we don't do that. In practice, we just almost do this in our head and say, oh, 3 plus what number gives us 5? Well, the answer is 2. But technically speaking, those are the steps. We find the anti plus 3. So we are adding 3 to x. How do we undo that? Well, subtract 3. So that's the anti 3 or the anti plus 3 to get rid of the 3, and that leaves the x alone. Now here, x is not a variable. What I meant by that is not a single scalar, it is a vector. I'm not putting the arrows for vectors because it is understood. But if we could find the inverse of a, then we could multiply the inverse on both sides on the left side of the equation, so a inverse b. And so those two give us the identity. So that's still a inverse b. And so x, but the identity times the vector x is the vector x. So that gives us a inverse b. And that would be the only solution. There wouldn't be any additional solutions. This would be the only solution. So that would be it in this ideal case. I hesitate to label this as case 1. I guess I'm going to call this case 1 of this video, but maybe, if you look at another book, this might be case 2 or case 3. So this is case 1 of this video only. That is an arbitrary number that I'm using right now. So the best case scenario is if the matrix involved has an inverse, just multiply out and you get an answer, and there's no extra answers. There's no more to it. Yeah, so that actually sort of contradicts, it doesn't, but sort of contradicts this. I'm going to tell you why it doesn't with an example. So let's do an example 1. Okay. Let's say we have the matrix 3, 2, 1, 1. There we go. Times x, y. And then I'm going to pick some random numbers such as, I don't know, 5 and 6. There we go, just 5 and 6. They're not too random. 5 was sort of random, although I prefer 5 because I'm just a fan of 5. 5. It's one of my favorite numbers. And then I'm lazy and I don't want to think of another random number, so I just move on to the next one. This one is a little bit by design. Anyway, does this have an inverse? Let's review a little bit about inverses, and let's use the Gauss-Jordan elimination method to figure out the inverse of this. Remember how we do that? So by design, well, of this example, I'm gonna use this method, but this method does not work for everything, every time. This is just one case if we are able to find an inverse. So let's work on this example for a little while. So inverse of this would be, well, let's write it down. So 3, 2, 1, 1. We're going to use the Gauss-Jordan elimination method to find the inverse. So there we have it. If we flip those two, we get, so this is, so R1 gets flipped with R2, and we get 1, 1, 0, 1, 3, 2, 1, 0. I'm going to move on to a new page. So then what what should we do here? We can subtract from R2 3 times R1. So we have 3 minus 3, 0, 2 minus 3, negative 1, 1 minus 3 zeros, still 1, 0 minus 3 times 1 is negative 3, and then the first row remains as is, 1, 1, 0, 1. And then we can add this row to that one to get that off. So we can do R1 plus R2. So 1 minus 0, 1. Well, 1 plus 0 rather. 1 plus negative 1, 0. 0 plus 1, 1. 1 plus negative 3, negative 2. And then we have, while we do that, let's multiply negative 1 times R2, or after doing that rather. So we end up with 0, 1, negative 1, positive 3. So we claim that the inverse of 3, 2, 1, 1, so 3, 2, 1, 1 times, well, I didn't mean that. We claim that the answer to the inverse, not the answer to the problem, the original problem. We're just trying to find the inverse there. So the inverse of this, we claim, is 1, negative 2, negative 1, positive 3. But let's double check. 3, 2, 1, 1, and then 1, negative 2, negative 1, 3. So 3 minus 2, 1, negative 6 plus 6, 0. 1 minus 1, 0, negative 2 plus 3, 1, which is the identity. So that checks. So the claim we made up here is correct. Okay. So the original problem of example 1 was 3, 2, 1, 1, find xy. So that gives us 5, 6. And the way we do that is by multiplying with this matrix on the left and on the left. So 1, negative 2, negative 1, 3 times 3, 2, 1, 1 times xy should equal 3, 2, 1, 1 times 5, 6. Now we just did this multiplication. That is the identity. The identity times xy is going to give us xy. And now let's multiply this out. 15 plus 12, 27. 5 plus 6, 11. There, so we have the solution. Xy has to be 27 over 11. And there's only one solution. That's it. There is no more. There's no more. The reason for that is because I'm not contradicting. Yeah, I'm sort of contradicting what I started saying here, that there's going to be a particular solution, which we can label it as this, as the particular solution, plus a whole bunch of solutions. But let's solve this problem, the equivalent to that problem. So we are still in example 1, and I'm elaborating a little more on example 1. Now, still within example 1, comma, okay, let's solve this equation. Xy equals 0, 0, which is the homogeneous equation corresponding to the non-homogeneous original problem. This was the non-homogeneous original problem, and this is the corresponding homogeneous. So the only difference is that the last column, the right side is 0, 0. That is called homogeneous. Okay, now let's think about this. Let's think a little more abstract. So ax, and by x we mean this vector. So I'm going to emphasize that by putting an arrow, equals 0. And by 0 we mean that vector. If we multiply both sides on the left by the inverse, then we have A inverse AX equals A inverse 0. And as you know, those two cancel off, and we end up actually with the identity X. Now, the thing here is that this guy is going to be 0. Anything multiplied with 0 will give us the 0 vector. And the size of the matrices is correct, so we have a defined multiplication. Now, it could be that um, one matrix is 3 by 2 or 2 by 3, and then it doesn't multiply well with the other matrices, which may not match the sizes correctly. But in this case, everything matches well. So what this is telling us, because the identity times x is x, is equal to 0. So we do have one solution. Actually, we do have a solution. So back to this example where we were, so in the homogeneous case, rather in the non-homogeneous case, back to the non-homogeneous case, where we had 3, 2, 1, 1, whoops, x, y equals 5, 6. The answer was, so after doing a bunch of work, we get to x, y equals, I think it's 2711. Yep, there it is, 2711. 2711 plus, and actually we could add a constant times the solution to the homogeneous equation upon a constant times 0, 0. So technically speaking, that would give us all the answers. However, this is unnecessary because 0, 0 times a constant, any constant gives us still 0, 0. So that's not going to be fruitful. And then, well, in the sense that adding 0, 0 to another vector is going to give us the vector anyway. So this is completely 100% unnecessary when we are writing a final answer, and that's why we just don't write it. So even though we could think as infinitely many solutions, not really, because we can add a constant times the homogeneous solution. Since the homogeneous solution was 0, we're not really adding anything, so we're just getting one solution. And that's why so I know this is a super long way to go back to the same thing. It almost seems like I'm making things much more complicated than it should be. I mean, we were finished back here, and that was already a stretch. Why am I going through this? Because this idea will not be simplified to that in many, many, many other examples. Many other examples. So that's why. Let's look at one of those examples. Example 2. Okay, so let's start with a matrix that is 3, 2, 1, 1. But now we have an extra column. I want to keep things simple. I'm thinking, let's put a 1 and a 0. So now we're going to solve this. So we have a 2 by 3. Our column here has to be 3. So x, y, z, or x1, x2, x3, as many books do, and rightfully so. And then I'm going to change this to, okay, so wait a minute. So 2 by 3, 3 by 1. So the answer will be 2 by 1. So 5, 6. Okay, so this is a second example, second matrix. We cannot find the inverse of this. If we did, let's see, it would be, I mean, it's some kind of a left inverse, which would not be equal to a right inverse. Can we do that? So that we end up with the identity. We would have a 3 by 2, maybe, but that's not the way to go about doing this problem. So we don't really want to investigate about inverses, because inverses in this case would be very, very specific. They would work in only some cases, not in general. And we want to have a general way of thinking of this. Okay, so let's start solving this by performing row operations. Yeah. So for instance, we can subtract the second row. Okay, so the second three times the second row from the first row to get a 1 here. Actually, now that I think about this, we can just switch those two around and that immediately will put us, so let's do that. Let's switch R1 with R2. And that's gonna give us 1, 1, 0, 3, 2, 1. X, Y, Z equals 6, 5. Remember what this means. Let's look at the second row on the original problem. X plus Y equals 6. So since we still want to preserve that equation, X plus Y equals 6, the 6 has to go now on top. So switching this row also implies switching those two rows. Okay, now let's, from the second row, we want to take away 3 times the first row. So the first one stays as is. See, we're going to carry X, Y, Z through the whole. So that's why many times we even get rid of that and we simplify and we actually put all of this into one augmented matrix. Okay, but let's keep it this way for now. Oh, wait a minute. Not 5 yet because we're still going to work with this. So we're using elimination, which means that whatever happens. So, okay, let's do this. 3 minus 3 of those is 0, which is what we wanted. 2 minus 3 of those is -1. 1 minus 3 of those, still 1. But then we have to do the same thing. 5 minus 3 of those, so 5 minus 18 is -13. Okay, now we're good. That's why we couldn't have the 5 here, because this column has to be affected as well in the same way as those columns or those rows, either way you think about it. So again, we add to that. So R1 plus R2 is going to give us 1, 0, 1. Okay. Add, you get 0, 1. The X, Y, Z is just there riding along. That's why, as you can tell, this is a little bit wasteful. I mean, the equation is correct, but it's a little wasteful as far as the operations go. And that's why oftentimes we work with the augmented matrix instead. So that means just the matrix, and we add this column, and then we work it out, and then we go back to the equation if you wanted to. So we're going to add -13 to the 6, and that is going to give us -7. And then we keep the -13. Oh, wait a minute. While we do that, we're going to multiply -1 with the second row. So that will cause us this to be 1. So we have 0, 1, -1, and then we got to multiply that by positive, well, by -1, giving us +13. Okay. Mind, sorry to keep repeating this again, but oftentimes, in fact, I'm just going to write it down. So there's more work to do, but I want to pause because there's more work to be done here. Or I want to show you something rather, the augmented matrix. So if you have 3, 2, 1, 1, 1, 0, the original matrix 5, 6. This is called the augmented matrix. And oftentimes this is just a simplified version of what we did of this first equation. Excuse me. And then we do row operations. And after doing row operations, we end up with a row echelon reduced form of the matrix, which would be 1, 0, 1, -7, 0, 1, -1, +13. And the only reason why we do that instead is because then we don't have to write all of those equations with the equal and the columns, but it is just a shorthand of doing all of this. I didn't go through all the steps because they would be just the same, but just be aware that that's what's going on with an augmented matrix. Okay, so now we got the augmented matrix. or this to be even better. Okay, and what is that telling us? That means that x plus z, oh, by the way, we got two pivots. That's important, two pivots. And so the rank of this matrix, the original matrix, is 2 because we got two pivots. Rank is 2. Any column that has no pivots, so this column has no pivots because the pivot is this, not, in order to end up with a pivot in our row reduced echelon form, we have to have zeros above and below the pivot. And there's no way to get, I mean, you could turn it into a pivot if you wanted to by adding this to this. So I guess this was a pivot. We could do that. We could have this, yeah, but then it's complicated. It gets because then this is not a pivot anymore. So those two would be the pivots, not this one. Yeah, we could do that, but it's not customary to do that. We typically leave the last variables as the free variables, which is what I'm leading to. So this corresponds to a free column if it doesn't have pivots. So that is one free column, which means that there's one free variable, which we will label as z, or is z in this case. What do we mean by that? See, this row says that x plus z equals -7. X plus z equals -7. This second row says that y minus z is equal to 13. All right, so that means that x is a function of z, negative z minus 7, and y is also a function of z, z plus 13. Okay, now we can go in two different directions with this. Whoa, two different directions. Let's go into the particular solution direction. Yeah. So if z equals 0, we obtain the particular solution x, y, z equals, well, 0 for this z, if z is equal to 0. So we pick a super easy number to drop in there. It is going to be 0. So x will be -7, and y will be +13. Okay, so this is one solution. Oftentimes we label this as XP, particular solution, a super easy particular solution. Why easy? Because we picked z to be 0. Now, there are many particular solutions, by the way. Another one, this is a parenthesis, another particular solution could be found by setting z equal to 1 or 2 or 3. So when z is 1, we end up with a particular solution, x, y, z, which will have 1 on z. Well, that's what we're doing. We're choosing z to be 1. So z is a free variable. It can be whatever it wants to be. It's free. It can go anywhere. Okay, but then that forces x to be -8, and y would have to be 14. So that's another particular solution. We prefer this one over this one because this one has 0 in it. Just like in calculus. Yeah. We prefer this solution over this one because this one has an extra term that is completely unnecessary. So within reason, the more zeros we have, the better. If we're going to achieve the same answer, the more zeros, so there's a zero here, the better. This one doesn't have any zeros at all. This one has a zero there. Now you could say, well, what if the zeros up here? Sure, that would work. We typically stick with the last variables as our free variables, if possible. Sometimes you cannot help it. Sometimes, you know, the middle one has to be a zero, not the last one. But if we can help it, then the last ones being zero are preferred. So this is our particular one. This is another particular one, but not as preferred. This is the one we prefer to have. Okay, but now what about the rest? What about, going back to the analogy of calculus, what about all the other solutions? So we did solve, remember, we're in problem number 2, example number 2. We're solving this system or this matrix equation, and we found one solution. The solution, -7, 13, 0. By the way, it's probably a good idea to check that our solution works. -7, so I'm kind of blending, I'm pretending that is here, and I'm gonna multiply to make sure we get 5 and 6. So that is -21 plus 26, because multiplying those two, that's 5, and 0, sure enough, that is 5. -7 plus 13 is 6, plus 0, 6. Okay, so that checks. That also checks. But this one is better for a particular solution. Okay, now what we're going to do is attach the homogeneous solution. So what is the homogeneous solution? Yeah, so the homogeneous corresponding problem is, okay, I got to remember our problem. So it has 3, 2, 1, 3, 2, 1, X, Y, Z. So we have a new problem, but instead of having 5 and 6, we're going to put 0, 0. That's what makes it homogeneous. So this is a different problem. 1, 1, 0, 1, 1, 0. Okay, now what did we do here? We flipped. So, and we flipped correspondingly here. We added one multiple to another, and then we added another one, then we multiply by -1. Well, so the process will be the same, yada, yada, yada. We're going to end up with 1, 0, 1, 0, 1, -1, 0, 1, -1, X, Y, Z. But those are zeros, and any row operations on zeros, it's still going to give us 0. Think about that. Okay, we flipped. Well, we flipped the zeros. Big deal. Still 0, 0. All right, we add one multiple to another row. Well, multiply 0 by anything, add it to 0, you still get 0 no matter what, whichever order we do it. We did that kind of thing again here, and we multiply by -1. So multiply 0 by negative. We still end up with 0. So that is the beauty of this. The row operations are going to end up being just 0, 0. Okay. So now let's look at the homogeneous solutions. In this case, we have that x plus y. This is the rank. The rank is 2. There is one free variable, one free column corresponding to one free variable. So whoops, not y, z. Yep, x plus z equals 0. And y minus z equals 0. That makes things really easy. That means that x equals -z and y equals +z. So the solution to the homogeneous equation is xyz equals negative z, z, and then z is z. If we factor out this z, we have z negative 1, 1, 1. But we can think of z as a constant. So this is really a constant times negative 1, 1, 1. So this is all the solutions to the homogeneous equation. Thus, the solution to 3, 2, 1, 0, rather 1, 1, 0, which is the original problem. 1, 1, 0, x, y, z equals 5, 6 is x, y, z equal to a particular solution. The particular solution was negative 1, rather negative 7, 13, 0, plus a constant times negative 1, 1, 1. There we have it. That is the set of all the solutions. So we have a constant, just like in calculus. The constant has to be multiplied with a vector, though. So this is many, many vectors. So if the constant is 2, we get a solution. If the constant is 3, we get another solution. Now, mind. And by the way, this is oftentimes labeled as XP for particular solution, and then XG for general solution, or H, sometimes XH for homogeneous solution. It depends on what book we may be using, what textbook we may be using. No. I meant this is, sorry about that. The homogeneous solution is here. The general solution is this one. So this one is referred as XG for general solution. This is one particular solution, and this is the homogeneous solution. Keep in mind, though, that if we put X, Y, Z as negative 8, 14, 1, negative 8, 14, 1, plus a constant times negative 1, 1, 1, we're still going to end up with the same solution. So this is accurate. It is not correct. So this is accurate, but not correct. There's a difference between accurate and correct. Accurate, but incorrect. Yeah. So if I say, what time is it? And then I answer, today is Monday. What I just said was not a lie. It is accurate. It's true that today is Monday because I'm putting this video together on a Monday. But my answer is incorrect because it did not answer the question, or not in the best possible way. I could have done it. If I say, what time is, if somebody asks, what time is today? And I said, well, it's the same time as yesterday at the same time, or it's the same time as yesterday, 24 hours ago. That is still accurate, but it is incorrect. That's not the question. Now, there's degrees of correct. So why this is not correct, even though it is accurate? Because this is not the simplest of them all. And what we mean by simplest is the one that has more zeros than all the other ones, in the sense that we have to have zeros for the free variables. This one doesn't have 0 for the free variable, so this one is better. Now let me show you what's going on. This is in geometry. This is a direction vector. This is just a spot, a point. Think of it as the slope and the y-intercept, so to speak. So that would be the y-intercept, so to speak. So yeah, what this is telling us is that in space, so geometrically, this is what's going on. You have a point, which is xp, and then a direction vector, which is, so this direction vector would be xh, the homogeneous. And then when we multiply by a generic constant, we have the entire line. So you can have double or triple in both directions. There we go. So we have a starting point and then the direction. So that's geometrically what's going on here. We have a starting point and then the direction. Can we start somewhere else? Sure, because we have the same, as long as this point belongs to this line. So can we start here instead? Sure. And then we're just starting at a different point and having a different direction. I mean, the same direction rather. So we end up with the same line. And that's why this answer is accurate. It is true that this line is the same as that line. We're just starting at a different point. But this is the best one because it has 0. Let me give you an analogy from Algebra 1. So this is just a side analogy. Say you have y equals 3x plus 5. Okay, so that's the direction, otherwise known as slope, and 5. So when we draw this, we go to 5, and then we have a direction 3, or slope of 3, same kind of thing. It's rise over run, so 3 over 1, so that is a direction, a rise over run. So we go this way. So we have this line. Yeah. Okay, nice, neat. Can we start the line somewhere else? Sure, 1, 8. So if we have y minus 8 equals 3x minus 1, will that work? For sure. Yes, it does work. Those two are the same line. Because I know the point, so what point goes through this line? The y-intercept is 0, 5. That's plainly seen here. Another point on the line would be 1, 8. You know, if you plug in 1, you get 1 times 3 plus 5, 8. Sure. If we start at 0, 5, this is the equation. If we start at 1, 8, that would be the equation. As you can tell, this is simpler. It has only 2 numbers. This one has 1, 2, 3 numbers involved. And then there is there's a few things going on here. Are they the same line? Absolutely. We're just starting at a different point. When x is 0, we're starting here. When x is 0, we're starting at the same spot, but it's just more convoluted. Yeah, this is actually worse because when x is, or when c is 0, we're starting at a different spot. But anyway, be as it may, you can tell this is more complicated. It gets the job done, yes. This is the point slope form of the equation of the line versus the slope to intercept. We, generally speaking, we prefer this one because it is the simplest form. It has a 0 in it. So this is perhaps not the best analogy, but it does hopefully the trick. That's why we prefer this. This is sort of the y-intercept. It isn't, but it is sort of that in the sense that it has more zeros. And we cannot help to have numbers that are non-zero. But this is the one with the most zeros. This one is definitely worse because it doesn't have zeros at all. So that's why we prefer this form. Okay. So that is example 2. Now let's start talking about example 1 and example 2. In example 1, what was the solution in example 1? Oh, 2711. Yeah, that has nothing to, we have only one solution. In example 2, we have infinitely many solutions. because we had a straight line and every point on the line is a solution. Every point on the line can be obtained by this equation. So if you want one point, just set C to be 0. There's, well, I keep going back to this point. This is the 1. If C is equal to 0, you have this. If C equals 1, you get another point, this one. If C is equal to 2, you get another point, a third point. If C equals 4, and C doesn't have to be an integer. Well, or a natural number, it could be negative, it could be a fraction, it could be pi, it could be anything, any real number. And every time you have a new real number for C, when you combine all of that together, you end up with another solution. And we have infinitely many, as many points as there are in this line. So example 2 has infinitely many solutions. Notice that in example 1, the matrix was nice and square. 3, 2, 1, 1. And we were able to have, see, it gets a little tricky because there's many kinds of examples. We were able to obtain the inverse by the Gauss-Jordan elimination method. This one, 3, 2, 1, 1, then we added things to it. Let me double check that that's what we added. Yeah. And that, by reducing this to row reduced row echelon form, so when we reduce this one, we end up with a nice identity. This one cannot get into an identity. The best we can do was, and I have to go back and see what we got, 1, -1 in the last column, 1, -1. And so that created a free zone, so to speak, which meant that now we can expand to many solutions as opposed to just a single solution. In this case, we had a single solution, 2711 was a single point, and that was it. Here, we got many solutions. All right, example 3. Notice that the examples take a long time. That is just the nature of linear algebra. 3, 2, 1, 1. And now we're going to add things here. On the other end, so on example 2, example 1, we started with these 4 numbers in that order. In example 2, we added numbers here on the right. And now we're going to add numbers on the bottom. I'm going to be consistent. I'm going to add 4, 3. And you'll see what I mean by that. So now we got a 3 by 2. So we need to multiply by 2 by 1. And let's go back to 5 and 6. So this is a new example. This is not the same example as example 1. I'm just being lazy and using the same numbers anyway. And this row was very special. I picked that row those numbers are not random. That's what I'm trying to say, not random. They were they were picked with care. So let's go through the motions as far as turning this into a row echelon form so that we can solve this equation. Oh, I just remember something about that I wanted to show you in example 2, but we'll come back to example 2 after we finish this one. So let me go through the motions here. Reverse. Whoa. Let me just double check. Yeah, the answer here has to have 3. We cannot have 2. We have to have 3. Let's say this is 11. And again, this is not random. Yeah, I made up this example, and I picked 4, 3, 11 very carefully. Otherwise, this example wouldn't work the way I wanted it to work. Okay. So yeah, the reason why I thought that we were missing something is because I was going to flip those 2, but wait a minute, which 2 am I going to flip? And there's only 2. It wouldn't make sense. So I'm going to flip those 2. initially. So we have 1, 1, 3, 2, keep the last one there. X, Y, 5, 6, 11. So the 11 is not random, just like the 4 and the 3 were not random. Actually, this is the one that is important that is not random. This one could be random, may or may not be random. It doesn't matter. So doesn't matter. Although that varies. It could matter if this is picked at random, then you can. So what I'm trying to say is those three are in concert. They are together. Yeah, they work together, or they may not work together. Anyhow, so 3 minus 3 is 0. So let's keep the first one alone. 3, 0. So we're taking away 3 of those to the second row. 2 minus 3, because we got to be consistent, is negative 1. 6 minus 3 of those, so 6 minus 15. 6 minus 15 is negative 9. Keep the 5 there. And then we're going to do 4 minus 4 of those, 0. 3 minus 4 of those, negative 1. 11 minus 4 of those, negative 9. Okay, we're going to add this to that. So we have, now, clearly it's more efficient to have the row echelon form. So we don't have to carry the X and the Y and the equal through each one of the steps. I'm not doing that. But row echelon form is the same thing. Oh, so let's add this to that, this row, to that row. So we end up with 1, 0. Negative 4. We're gonna work with the last row. We're gonna subtract from the last row the second row because they're the same. So when we subtract, we get 0, 0. So, and we're gonna end up with 0 here. Negative 9 minus negative 9 is gonna be 0. And then we're gonna multiply this row by negative 1. So we're gonna end up with 0, 1, 9. Okay. So what does this tell us? This tells us that X is negative 4, Y equals 9, and that's it. Yeah. And then 0 is equal to 0, which does not add more information. Actually, that it tells us that. 0 plus 0 is 0, which is equal to this 0. So because this is an identity, we don't add more information. So we have a solution. The solution is a single solution. XY is just negative 4, 9, and that's it. There's no more to it. Yep. Yep. Example 4. I'm going to piggyback on this example. 3, 2, 1, 1, still 4, 3. XY, whoops, XY. 5, 6. Now I'm going to change that 11. I'm just going to change it a little bit. 12. Oh, okay, let's piggyback on this. Same procedures. we're going to end up on this matrix with 0, 0, 0, 1, 0, 0. Same thing. So, whoops. So we're going to yada these steps, and we're going to end up with 1, 0, 0, 1, 0, 0, x, y equals. It's not going to be so easy to yada the rest because we have to go through the motions. So first we flipped. Kind of let me work with the first column. So here's a little bit of the yada. We started with 5, 6, 12, 12 this time as opposed to 11. And then we transformed that into, so the first thing we did is flipped 5, 6, 12, and then just realized I did something wrong here. Let me fix, sorry about that. You are probably screaming through the screen. Yeah, we flipped those two, but I didn't flip those two. Barnacles 5. And then that's why those numbers didn't match the other numbers that we had in example 1. And then we did 5 minus 18 is negative 13. And then 11 minus 4 times 6, so 11 minus 24 is negative 13. So this guy should be positive 13. And that still remains as 0. So the answer should be negative 4. Well, what did we do with the first guy? So 5, 6. So this should be 6 initially. When do we get rid of this 6? When we are adding the negative 13 onto the 6. And that's going to give us negative 7. There we go. So this guy should be negative 7, positive 13, and 0. Well, 0 equals 0. So that should be negative 7 and positive 13. And now it's fixed. I'm going to check with my first example. Which doesn't match, but let's just double check and see if it works. We have the problem here, and let's make sure that this guy works. 3, 2, 1, 1, 4, 3, multiplied with negative 7, 13, and let's see what we obtain. Negative 21 plus 26, 5. Negative 7 plus 13, 6. Negative 28 plus 39, 11. It works. So this is the correct answer to example 3. The reason why I had to go back to example 3 is because as I was following the steps, I was realizing I omitted switching the 5 and the 6. So the lesson learned is just do the steps one by one anyway. Example 4, 3, 2, 1, 1, 4, 3, x, y equals 5, 6, 12. Okay, let's do the augmented matrix. 3, 2, 5, 1, 1, 6, 4, 3, 12. Switch row 1 and row 2, switch them. So we have 1, 1, 6, 3, 2, 5. I guess there is value in doing the augmented matrix because I can keep track of everything. 3, 12. Then let's do row 2 minus 3 times row 1, row 3 minus 4 times row 1. So 1, 1, 6 remains. 3 minus 3, 0. 2 minus 3, negative 1. 5 minus 18, negative 13. 4 minus 4, 0. 3 minus 4, negative 1. 12 minus 18. No, 12 minus 24. Negative 12. Yep. Okay. Now let's subtract. So in the next step, we're going to add R1 plus R2, and we're going to take R3 and take away R2. So R2 is going to remain as is. So when we add, we get 1, 0, negative 7. When we add on here, or rather when we subtract, we get 0, 0, 1. Let's multiply the second row by negative 1. And we may be thinking, oh, beautiful, we get a nice diagonal, so this is consistent. Because we may be thinking, oh, we can just add this there, add this here. Sure, we could actually do that and actually end up with a nice idea. Let's just do it. We can take the last row, well, row 1 plus 7 times row 3 and row 2 minus 13 times row 3. So we end up with a nice identity. 1, 0, 0, 0, 1, 0, and then 0, 0, 1. But mind, the last column is the column of the constants. That's the first columns are the columns of the variables. So translating this into the system of equations, what this is telling us, well, let's write it first. 1, 0, 0, 1, 0, 0 times x, y is going to give us 0, 0, 1, which looks not very bad, but this is telling us that x is 0, nothing wrong with that. Y is 0, nothing wrong with that. 0 equals 1. Here is where we have a problem. What? That's a contradiction. That means that there is no solution to the original problem. Our original problem has no solution whatsoever. None. Nothing. Zip. No solution. So we can have no solution at all. Example 4. Examples 4. No solution. Example 3. And example 1 had one solution. They both had one solution. 3 and 1. Exactly. One solution. Example 2, that's the one with the free the free variables, had infinitely many solutions. I'm not going to do a concrete example, but I just want to give you an idea of what's going on with this 3, 2, 1, 1. Remember? And then in one of the examples, we added more columns. On the other examples, we added more rows. So we can add more columns and more rows. With this is my original example 1. And you don't have to add only 2. You can add 3, 1, whichever number of columns and rows. It doesn't matter. So if we end up with zeros here, if eventually, by doing row operations, this boils down to, let's actually go through some of this, 1, 0, 0, 1. But then you end up with zeros across here. And we don't have to have 3 zeros, whatever number of zeros here. That means that whether we have a solution or not depends on B. So, and then we have the X vector. I'm just going to call it X vector equals B. Yeah, let's not put the parentheses. There you go. Because if we have an inconsistency on B, as the only thing I changed from example 4 and example 3 is that this 11 turned into a 12. That was the only difference. And that caused us to have a nice, solid solution to no solution at all. There was no solution because there was a contradiction. We arrived at a contradiction, and so there's no solution. So if you have a bunch of zeros here, that means that whether we have a solution, a consistency or not, depends on B. Because if the last rows, where this corresponding to the 0 rows in here, are not consistent with the rows up here, then we have a problem. Yeah. So B has a lot to do with whether this has a solution at all or not. Okay. If we have more columns, then all that is going to do is that if we have a solution, we will have many solutions, potentially many solutions, because then we will have more free variables. So in this particular example, I'm assuming that the rank stops at 2. But you could stop at 3 too, but let's just pretend that it stops at 2. That means that if we had a 5 by 5 matrix, for instance, or a 4 by 5 in this case, then we would have 3 free variables. And so instead of having C X homogeneous, well, there would be 1, but then there would be a second 1. So we have to label as 1 and 2 plus E, where those are constants. Yeah, X homogeneous 3. Yeah. So how many freedom or free columns we have tells us how many parameters we have to include into our general answer. And then we have a particular answer, which is the simplest one that solves the problem completely. And that gives us our general answer. The one thing I wanted to bring back from example 2, yeah. So back in example 2, remember what we did? We found a particular solution. -7, 13, 0. negative 7, 13, 0. And then we found the homogeneous solution. Still remember, negative 1, 1, 1. And then we consolidated them. So the general solution is negative 7, 13, 0 plus constant negative 1, 1, 1. Okay. That's the way we did example 2, which is the most general way of obtaining all the solutions. There is sort of a shortcut. It's not a shortcut. We could have gotten that before getting to this point. And it is important to realize there's about at least 2 ways to get to this. Now, at one point when we were working on this example 2, we got to this point, to these equations. X plus z equals negative 7. X minus z equals positive 13. That meant that x equals negative 7, z rather, minus 7, and y is z plus 13. So really, we could have just written the answer as negative z minus 7, z plus 13, and z. We could have written the answer this way, and you can just change the z with a constant, and that will be okay. But let's break this down. This is the same thing as negative z, 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 plus the vector negative 7, 13, 0. Negative z minus 7, z plus 13, z plus 0. And then we can factor that z out and have z times negative 1, 1, 1 plus negative 7, 13, 0, which is exactly what we arrived to by combining the homogeneous solution and the particular solution. This is the particular solution, and this is the homogeneous solution. This is just written differently. This is very much like the equation of the line, by the way. Pretend this is a slope, so it's like a y equals slope mx plus b. This is our b. It is very much the same. Now, if you had two free columns, then you would have perhaps z times this, y times another vector, and then you still have your initial point where we start. All right. With this, we will finish this video. Hopefully this is helpful.